In the outer solar system there exist many unassuming worlds. Worlds like Callisto, Mimas, Oberon or Proteus are often overshadowed by their more spectacular neighbors. From a world-building lens, it is sensible to put in some generic worlds for your project too, as doing this will help highlight the more unique ones you add. For Project Espa, currently all inner moons of Manta are very spectacular worlds, to the point where, as of yet, we have not yet added any unassuming worlds. So today, let's be bold and see if we can make a quote-unquote boring world for this purpose. Hello everyone and welcome back to Project Espa. My name is Yichi Online and in this series I document the progress on my worldbuilding project, Espa. Thus far in the series we've started out with the astronomy of Espa's star system, a wide separation trinary star system with the sun-like star Ojor at its center, which is being orbited by two red dwarfs at a far distance. Ojor itself has 9 planets, the fourth of which is the gas giant Manta, the system's main Jovian shepherd, which is over twice as massive as Jupiter. Manta possesses an extensive lunar system consisting of 6 major moons. Over the last few episodes we have finished the resonant inner 4 of those. The hypervolcanic world of Ideme, the exotic life-bearing world of Tora, the cryovolcanic ice world of Sanu, and last episode, the magnetic world of Hera. Today, we continue on beyond this resonance chain and discuss the 4 last of Manta's moons, the dark world of Tolu. When I built the first iteration of the Mantonian system in 2017, Tolu, originally called Teth, was a multicolored ice world based loosely on Hoth from Star Wars. Teth was slightly larger than Mars, but 3.5 times as massive, giving it a broken density of 11 grams per cubic centimeters. Like, seriously, I don't know why this is a pattern with my old moons. This thing was literally as dense as lead and I did not see an issue. Anyways, at least unlike the other old moons, Teth was cold, whereas the old versions of Ideme, Tora, Sanu and Hera all employed miraculous methods of having moderate temperatures, Teth was 85 degrees below zero. This was still way hotter than its effective temperature of negative 179 degrees, but it's a little bit of progress, I guess? It also had a dense atmosphere consisting mostly of neon gas and some oxygen? Okay, fair point on the oxygen, but neon? I don't know what I was thinking. And other than that, Teth was pretty featureless, I guess. So to sum it up, Teth was a highly unrealistic ice world that I left pretty shallow with details. Looking back on it today, I don't think it will have to be redone ground up like Sanu and Hera. But, nevertheless, some major work is in order here to transform Teth into Tolu. Alright, so whereas we basically completely redid Sanu and Hera last 2 episodes, for all intents and purposes, Tolu will still be an ice world. Not just because I think that's a cool concept, but because at this distance from Manta, logically, it kinda has to be. Remember that the mass fraction of volatiles, those being mainly water, will only go up the further a moon is from its giant parent. Tolu, which is over 1.6 million kilometers out from Manta, could be our first world of which half its mass constitutes water ice. Of course, this will have major ramifications for what kind of world Tolu will turn out to be. In world building, giving every world its own special trait can be a noble goal. But I think you also need to be careful about oversaturating your system. We already did some really impressive things to spice up the resonant moons. So for this one, my goal is to kinda just follow the math and see where that takes Tolu without doing anything wacky with it. Partially, this is to make the other moons stand out more by contrast, but I also think it's good for the system's realism to add a few unassuming bodies, where we don't force any traits onto them. Before we actually dive in today, I think it's worth taking an extra moment to gander at Tolu's orbit. Because if you've been paying attention in the last couple videos, you'll notice it's in a bit of an awkward spot. Do you see why? Alright, I will elaborate. To recap, the inner 4 moons of Manta are resonant bodies, with Ideme orbiting Manta 8 times for every 4 times Tora does, for every 2 times Sanu does, for every once Hera does. This stabilizes these orbits by distributing tidal energy between these moons. Tolu, though, is not a part of this chain and as such does not benefit from these distributing forces. But there's a major asterisk there. Hypothetically speaking, if this quadruple resonance chain went on to include a 5th moon, it would be located roughly 1,950,000 kilometers out, orbiting once for every 2 orbits of Hera. Although far from Manta, Tolu orbits well short of this distance at 1,622,000 kilometers out, and thus is not a part of this chain. But at this distance, its orbital period is actually very close to resonating 2 to 3 with Hera's orbit, currently being roughly 2 to 2.954. If only Hera's orbit had been a bit closer to Manta, this resonance chain could have been longer. In previous videos, I've explained how resonance chains slowly, over time, migrate outwards from their parent planet, meaning in the past Hera's orbital period was shorter. Short enough that in the past, possibly the quite recent past, it should have been resonating 2 to 3 with Tolu. If this was indeed the case, that means a past 2 to 3 resonance between Hera and Tolu existed and was then broken. But how could that be? Aren't resonances supposed to be super stable? Well, yes, but there is some nuance there, as in that some resonance configurations are more stable than others. Due to how entropy works, lower resonances are more stable than higher ones. For example, you could have objects resonating 11 to 17, but that's not gonna be as stable as 3 to 7 or 1 to 3. And out of all these resonances, 1 to 2 is going to be the most stable one. So, when we have a past situation where Hera is resonating 2 to 3 with Tolu and 1 to 2 with Sanu, eventually the resonance with Sanu is going to be dominant. Especially if we consider the chain with Sanu also extends to Tora and Ideme. Resonance migrations are complex. In the Jovian system, the moons Io, Europa and Ganymede all have varying migration rates. Io, for example, is currently thought to be migrating inwards, while Europa and Ganymede are migrating outwards at 2 and 11 centimeters per year respectively. What is going on here is that Io, being closest to Jupiter's center of mass, experiences the most tidal forces trying to push it outwards. However, due to being in a resonant chain, most of that force is transferred to the outer moons, meaning that Ganymede, and in Manta's system Hera, will be the fastest migrator. That's a very scientific way to say there is no linear correlation between orbital distance and orbital periods. And I promise there's very fancy math behind this with torques and angular momentums and yada yada yada, but I did promise to keep things simple today. So in the spirit of soft realism, let's say that because Manta is so massive, its tidal forces exerted scale up, and thus so will the migration rates of its moons. Assuming an outward migration rate of roughly 8 centimeters per year for Hera, this means Tolu could have been dynamically coupled to Hera as little as 160 million years ago. Not all that long ago on astronomical timescales. The cool thing is, I did not actually plan for this, but it's a very cool thing that just rolled out of the orbital maths. It aligns well with our goal today, and in world building these are the sorts of opportunities we need to seize upon. What often happens when a body goes through orbital disruptions, like escaping a resonance, is that its orbit will become more eccentric. And even though 160 million years will have passed since this event, I still feel it would make sense to give Tolu the highest eccentricity of all Manta's moons. Let's say 0.1. This doesn't really do much, but it does augment the believability of a past resonance scenario to me. So let's put it in, why not? Tolu is the second largest moon of Manta. Measuring 5,200 kilometers across, it is only about 300 kilometers smaller than Hera. With just over 2 lunar masses, Tolu achieves a low density of just 2 grams per cubic centimeter. Like established in the previous episodes, these low density bodies are composed largely of ice. The lower the density goes, the more ice the body will have, and in the case of Tolu, we're looking at a moon of which roughly half its mass is water ice. Mustering only a low surface gravity of 0.15 Gs, Tolu has not held on to any atmosphere to speak of. Its surface-bound exosphere exerts barely a picobar of pressure and consists mostly of oxygen. With such a trace atmosphere, there is little heat retention on the surface, and temperatures on Tolu usually peak at 175 degrees below zero. Being a distant, non-resonant body, the tidal acceleration upon Tolu is roughly 33% lower than it is on Ganymede, meaning that little internal heating is generated. But that hasn't been the case for very long. Until a few hundred million years ago, Tolu was resonating, which significantly delayed core cooling. As a result, even today its core maintains a liquid outer layer, which generates the moon, its own very weak magnetic field. From there on out, Tolu's composition would be very similar to that of Hera, with a transitional mantle made up of mostly rock at the bottom and exotic ices at the top. In turn, the mantle would be covered by a brine ocean hundreds of kilometers deep, at the bottom of which the immense pressure would compress the brine into various forms of exotic ices, while at the top the bitterly cold surface temperatures would freeze it over completely. From space, Tolu is hard to spot. Its surface has an albedo of only 0.21, making it among the darkest bodies in the Ojoran system, easily blending against the dark background of space from a distance. Much like with Hera, Tolu did have ice tectonics in the distant past, but they have since shut down billions of years ago, leaving behind a patchwork of younger and older areas on the surface. Outside the resonance chain, Tolu is more susceptible to meteorite impacts than the inner moons, and since its geologic processes shut down pretty early in the moon's 5.8 billion year history, it has accumulated a cratered surface. Many of the impacts having splashed dirt and dust all over its once bright icy surface, causing the low albedo. Tolu also features a couple of ray craters, which are younger, larger craters that have penetrated more deeply, splashing up fresh icy material, leaving behind these bright radial ejecta structures. Some of these ray systems measure several hundreds of kilometers across and are records of some truly violent impacts. Manta's powerful magnetosphere subjects its interior moons to beyond lethal amounts of background radiation. And despite Tolu's 1.6 million kilometer distance to the giant, even here it is not safe. Using our radiation formula, we can estimate that even at this distance, Tolu is subjected to at least 8 millisieverts of radiation per day. Which may be nothing compared to what is experienced on some of the inner moons, but this dose is still lethal to the unprotected within weeks. Which just goes to show how incredibly strong of a magnet Manta actually is. In our solar system, Ganymede is the only non-planetary, non-star body with a magnetic field of its own. But in the Ojoran system, much like Hera, Tolu shields itself from some of the radiation with its own magnetic field. Some, but not a lot. In Hera's video, I said its field, Hera's field, could block as much as 95% of the incoming radiation. While that statement isn't wrong per se, this value, which I got from Ganymede, applies specifically to the beta radiation, which is electrons, small particles easily ensnared by magnetism. The vast majority of incoming protons would not be blocked. You need something like an ozone layer for that, which neither Hera or Tolu has. So the overall effect of this field would be minimal in terms of shielding these moons from radiation. To be clear, this doesn't break anything for Hera, but I do think it's important to clear up, because its radiation dose, as well as Tolu's, would not be dramatically lowered by the presence of a magnetic field that primarily shields against beta radiation. With that in mind, Hera's new radiation levels increased to 150 to 200 millisieverts per day, with only 30 to 40% of the radiation blocked. And on Tolu, the much weaker, half a microtesla strong field would probably, even on a good day, only block some 10% of the incoming radiation, resulting in an overall total dose of some 7 millisieverts per day. Still sufficient to kill in a matter of weeks. Tolu is the fifth moon of the gas giant Manta. At a distance of 1.6 million kilometers, it orbits Manta once every 8.5 days and is tidally locked. With a diameter of roughly 5200 kilometers, it is the second largest of Manta's satellites, containing a mass roughly twice that of the moon, roughly half of which being water ices. It has a gravity of only 0.15 Gs and no atmosphere to speak of, making for an airless, desolate world. Tolu has dark, patched and grooved terrain, formed by cryotectonic activity early in its history. Even though these processes shut down billions of years ago, their evidence remains. Without these processes, Tolu's surface has begun accumulating craters, even featuring some bright ray crater systems. Although a non-resonant world today, Tolu in the past was synced 2 to 3 in resonance with Hera, before decoupling from it about 160 million years ago. This past resonance delayed core cooling enough that even today the moon possesses a weak, fleeting magnetic field which provides only some 10% shielding against incoming radiation. Manta, which appears 10 times as large as the full moon in its sky, shines about 7 millisieverts of radiation per day onto the world, making it an irradiated, cratered wasteland. Let's get to the comment of the day, which is by Heronixian Guy. A little question here, will we see a Titan-like moon or something like it in the Ojoran system? Now I know Nakwa's nitrogen moon exists, but what about a full-on Titan analog or something like it? Yes, I should probably address the old Espa versions. So I did a whole video on those at the start of this series, but in case you missed it, I started working on Espa all the way back in 2014. And over the years, I've made a lot of changes. Some quite small, others quite big. Because I enjoy record keeping, I've kept all the old documentation, like the Worldcraft videos and the old wikias online, but I do understand that as we build up a new continuity in this project, that might get confusing. That's also why I start all the Espa videos with a short history segment to officially decanonize the old versions, but maybe let me know in the comments if you find this confusing or what I should change if so. I'd love your feedback on that. Annaba, which is the nitrogen world you are referring to, existed in the old versions as a moon of the ice giant Nakwa. Putting in a Titan-like world would be cool, but I don't want to get ahead of myself and say anything about the other planets or moons while I'm still working on the Manta system. Otherwise I'm just gonna lose track of things. So if or where I will put it in is a question I will get to in time, I guess. Definitely a cool idea though. Anyways, thank you guys so much for watching. And if you enjoyed the episode, go show it some love by hitting that like button. And if you haven't subscribed yet, you know what to do. Smack that subscribe button for more worldcrafting. For the next episode, we're gonna start to wrap the Montan system up with its last major moon.